In this example, we'll actually use the idea of finding an instantaneous rate of change to find the instantaneous velocity of an object that's moving. Okay, so let's start with this illustration. All right, a person at the top of a 300-foot tower throws a rock upward with an initial velocity of 60 feet per second. The position of the rock at time t in seconds is given by the function s of t. S typically stands for position, is equal to negative 16t squared plus 60t plus 300. Okay, so we want to make sure, first of all, that we have the idea of what this function is telling us. All right, this function, so first of all, is to find the position of the rock after 1 second. Well, after 1 second, t will be 1, so we'll have s of 1, which will be negative 16 times 1 squared plus 60 times 1 plus 300. That will be negative 16 plus 60 plus 300, and that will be 360, excuse me, 360 minus 16, 360 minus 16 is 344. Okay? All right, let's take a look at the idea here. Okay, so we have this rock, okay, and it starts at time t is equal to 0 at 300 feet. At time, as we go along here, when the time gets to be 1, all right, we've gone up to 344 feet. And so that's where it is, the rock has moved vertically upward. Notice that this curve doesn't represent the path of the rock. The rock is only going straight up, coming straight down. The height of this position, the y value, as it were, represents the position, how high the rock is, and the horizontal value, the x value, as it were, represents the time t in seconds. It really is a t value and an s value, not an x value and a y value. But that's what we're used to thinking about. So now let's take a look. Let's find the average rate of change. And I think I have a mistake here. The average rate of change, no, I guess not. The average rate of change in the average velocity of this object, all right, on the interval from t is equal to 3 to t is equal to 6 seconds. So here we have an interval from 3 to 6 seconds. Okay, and I've done these computations ahead of time so that I wouldn't make a mistake. If we find the position of the rock at time t, at times 3, that would be s of 3. So we'd have negative 16 times 3 squared, negative 16 times 9, plus 60 times 3, plus 300, and that turns out to be 336. At time t is equal to 6, at the other end of the interval, okay, we have, and again, that would be negative 16 times 6 squared plus 60 times 6 plus 300. It turns out to be 184. So notice that the average velocity is the average rate of change in position with respect to time. That's how we calculate speed. There is a difference between speed and velocity. But so if we calculate the average, the rate of, or the change in t, that would be 6 minus 3. That would be 3. The change in s is going to be 84 minus the final value of s minus the initial value, 336, and that's going to be a negative 252. And now if we take to find the average velocity, if we find the average rate of change in s with respect to t, change in s on the top, change in t on the bottom, that would be negative 252 divided by 3. If you divide that out, you get negative 84. So this average rate of change, or average velocity over this interval in time, is negative 84. Let's take a look at this idea. Okay, if we do this, all right, notice that when we get to the place where time 3 is, all right, notice at time 3 we're at 336. Well, if we've gone upward and on our way back down, all right, and so we'll have that point there, 336, and then if we, then I think I've gone too far. Then if we go to time t is equal to 6, all right, at that time, all right, the height is I have to look back to see what it was, is 84, okay, is 84, okay, and then if we would take this point here, again, is 684, this one is 336, and if we would take the rate of change in y with respect to, or s with respect to t, we'd get a negative 82. Notice this, what we've really done, another way of looking at this is we've calculated the slope of this secant line. Oops, sorry about my dog, somebody's just gone by. All right, now what we'd like to do is we'd like to do the same thing here, but let's calculate the average velocity over the interval from 3 to 3 plus delta t seconds, so 3 plus some rate of change in 3. Again, I've written these out because they're kind of long. So we have our interval, the left end is 3, the right end is 3 plus some change in time, okay? And so in this case then, excuse me, we can think of the delta t kind of like the h that we had before. So if we go from 3, t starts at 3 and t ends at 3 plus delta t, how much did t change by? Well, it changed by delta t. All right, and at 3, the position, the height of the rock was 336. At 3 plus delta t, it's going to be, filling in the formula here, all right, 3 plus delta t for t would be negative 16 times the quantity, 3 plus delta t, in place of the t here, 3 plus delta t squared, plus 60 times t, but in place of the t again, 3 plus delta t, plus 300. So, excuse me, so the change in s is going to be the value of the s at the right end point, negative 16 times 3 plus delta t squared plus 60 times 3 plus delta t plus 300. The position at the final value, 3 plus delta t, minus the position at the beginning value at 3 itself, 336. That would leave us then with an average rate of change of this expression, all right, the change in s divided by the change in t, okay, which was just delta t. So this would give us the average rate of change in s with respect to t over the interval from 3 to 3 plus delta t. Okay. Let me make another copy of this. I don't know if I have it down below. I guess I do. All right, to find the instantaneous velocity, all right, we would take the limit as that average rate of change as the right endpoint of our interval the right end of the interval goes to the left end, or as the 3 plus delta t approaches 3, well, if 3 plus delta t is approaching 3, delta t must be going to 0. Again, sort of like the h before. So it would be the limit as delta t goes to 0 of this average rate of change, all right, in s with respect to t. Now, I've done some of these computations ahead of time just to make sure that I wouldn't make a mistake while we were doing this, but notice what we have here. All right, if I expand this out, all right, multiply through, I'd have a negative 144 times a negative 96 delta t minus a 16 times delta t squared plus 60 times 3 is 180. 60 times delta t is 60 delta t plus 300 minus the 336. This is going to be the same as the limit as delta t approaches 0 of, well, let's see, if I combine all the constants, they actually subtract out. I'll get 300 plus 180 is 480, and negative 144 minus 336 is negative 40, so these all subtract out, and I'm left with this negative 96 delta t minus 16 delta t squared plus 60 delta t. Everybody has a delta t in the numerator in what's left, so I'll have delta t times the quantity negative 96, right, minus 16 times delta t plus 60, and that will be divided by delta t. The delta t's cancel, and I'm left with the limit as delta t approaches 0. Well, the negative 96 and 60 together are negative 36 minus 16 times delta t. As delta t approaches 0, well, we can see what's going to happen. This last term is going to become 0, and so we get a negative 36. Notice this will be a negative 36 feet per second. That will be the actual speed, all right, or velocity that's happening, all right, right at time 3. Right at times 3, when the rock is 3 seconds into its flight, and it was, I believe, 336 feet high. Let's see again what's going on here. We're changing the change in time, all right, from 3 to 3 plus delta t, and we're letting delta t get smaller and smaller and smaller and smaller. Notice right now delta t is 1 about, and notice the average velocity over this interval from 3 seconds to 4 seconds about negative 51 feet per second, right? And as we continue to let delta t get closer and closer to 0, all right, we have, all right, an instantaneous velocity right at this point in time, an instantaneous velocity of negative 36 feet per second. The negative 36 comes from the fact that the rock will be going downward at that time. The rock will be traveling downward. This is like a speedometer on the rock, all right? Your speedometer in your car tells you how fast you're going at a particular time. The instantaneous velocity tells us how fast this rock is going at a certain point in time. In this case, how fast the rock is going at 3 seconds into its flight.